In this problem, we are going to use the chemical potential framework to derive a model to describe a colligative property. Specifically, what we want to do in this problem is we want to derive a formula to describe the shift in freezing temperature of a dilute solution. Right? So you can imagine you have water that has some amount of salt in it. Okay? That's what we want to do in part A. And then part B, we actually want to go out and calculate the freezing point temperature of salt water or seawater that has a salinity at 3.5%. And then we're also given some information about the enthalpy of melting. Okay? And so, for these types of problems, it's useful to sketch out a diagram. And so, in this case, because we're looking at freezing point depression, the diagram I have has on the bottom the mixture. So in this case, you can imagine it as water with some sort of solute in it. And then on top is another phase that's the solid. In this case, we'll say it's ice. And so to approach these types of problems, we first need to make a couple of assumptions. Okay? All right? The first assumption we're going to make is that our mixture, so this part, is dilute. Right? And so essentially, we would say that the mole fraction, so the mole fraction of the salt in the mixture is basically 0. And the reason for making that assumption is so that we could consider that the excess partial molar Gibbs energy of the solute is also 0. All right? So we won't have to account for any sort of very strong non-ideal interactions in the system. The second assumption we're going to make has to do with the solid phase, the ice. And we're going to say that the ice is just going to be pure water, right? Such that there's absolutely no solute or any salt in there. Okay? The third assumption we make, and we're going to have to anticipate this, is that the enthalpy of melting, so going between the solid to the liquid phase, that enthalpy is going to be a constant with respect to both the mole fraction of the solute in the system and also temperature. All right, so if delta HM shows up, we're just going to treat it as a constant. Okay? So those are the assumptions we're going to make to help simplify our analysis. And so for approaching this type of problem, there's a couple of basic steps that you could follow. The first step is you need to define your equilibrium criterion. Okay? So what are the rules that need to be satisfied in order for two phases to coexist? Okay? And so, for a mixture, our equilibrium criterion are going to be the following. The temperature of the solid ice phase has to be the same as the temperature of the liquid mixture. The pressure in the ice phase needs to be equal to the pressure of the mixture. And then the third criterion is that the chemical potential of a species in the ice phase has to be equal to the chemical potential of a species in the mixture phase. Okay? So those are just all of our chemical or our equilibrium criterion. Okay? So that's the first step, define those. And then the second step is we need to define a model to describe our chemical potentials. Okay? In general, if you're dealing with a mixture, the chemical potential mu sub I can be described like this, where you have your standard state chemical potential plus an RT ln of xi term, right? That essentially accounts for the entropy of mixing. And then you have your excess partial molar Gibbs energy term for species I. Okay? So that normally accounts for any non-idealities. But because, we're dealing with a dilute mixture, we're going to assume that this excess partial molar Gibbs energy term is negligible. Okay? So we're not going to worry about it for these types of problems. Okay? Now, to derive the freezing point depression, rather than starting with the chemical potentials on the solute phase, it actually strategically makes more sense to define your chemical potentials, or to focus on the chemical potentials of the water species in this problem. Okay? All right, so what we're going to do is let's look at water. And the reason we're going to do that is because, we made this assumption that the ice is a pure water solid, right? That this is pure water. And so the water species is the only species that's in both phases, okay? So water, because it's in both phases. Okay? All right, so first we're going to define the chemical potential equation for water in the solid phase. And so mu water in ice is going to be equal to the standard state chemical potential. So I'll just write it out here, plus RT ln of water in the ice phase. Okay? All right, and so here, because we're assuming that the water, or the ice, is pure water, that means this mole fraction is 1, right? So this is 1. And the natural log of 1 is 0. So this entire term goes away. So that's the first simplification that we can make. All right? And then when it comes to the standard state chemical potential, here what we do is we could set it to describe to be pure solid ice. Okay? All right, such that, after this term cancels out, what we have left here is the standard state chemical potential. But then we could rewrite it as just describing the chemical potential of pure water in the solid phase. Okay? And you'll see why that's important in a bit. Okay? All right, so that's the solid phase chemical potential. Let's now do the liquid phase chemical potential. So here we're going to look at water in our mixture. Right? So this one actually does have salt in it. Right? And so here, once again, we have our standard state chemical potential, and then RT ln XW mixture. Okay? In this case, the mole fraction of water in the liquid phase is not equal to 1, so we're going to keep this around. Right? But one other thing that we're going to do is we're still going to need to deal with the standard state chemical potential. And so here, because we're dealing with the liquid phase, we're going to set this to be, or to represent, pure liquid water, such that we could write our chemical potential equation like this. Okay? So for the solid, we're just left with the chemical potential of pure solid water. And for the liquid phase, we have the chemical potential of pure liquid water plus this RT ln of XW term. Okay? All right, so we defined our chemical potential equations. The third step is now we need to apply our equilibrium criteria. All right? Specifically, we're going to apply the fact that the chemical potential in the ice phase is equal to the chemical potential in the liquid mixture phase. All right? And now that we have these equations to describe the chemical potentials, we could plug those in. So here, the chemical potential of the ice phase, we showed is just equal to that. So we'll write that, or actually I'll write it like this. First, we have the chemical potential of the ice phase is equal to the chemical potential of water in the mixture phase, right? So now we plug in for the ice phase. So we have mu water ST, and we plug in for the mixture phase. Water liquid plus RT ln of XW mixture. Okay? All right, and then we'll rearrange the equation so that we get this expression. Okay? And so by applying our equilibrium criterion, we now have a relationship between the differences in the chemical potentials to the mole fraction of water in the mixture.